Welcome to AERO 1020, presentation number 3 on the flight environment. The atmosphere around the Earth is made up of gases surrounding the Earth, and the composition of the atmosphere is about 78% nitrogen and 21% oxygen. And then the other 1% is other gases like water vapor, carbon dioxide, and ozone. The atmosphere extends from the surface of the Earth up to about 27 nautical miles, but it's very thin when compared to the average radius of the Earth, which is about 3,438 nautical miles. 99.9% of the atmosphere's mass lies below this level. So as you can see in this figure, 50% of the mass in the atmosphere lies below just 18,000 feet, from sea level up to 18,000. And then another 40% up to 53,000. It's very thin above 53,000. You only have another 9.9% below 164,000, so for a total of about 99.9%. The different layers of the atmosphere are characterized by different changes in temperature, and we divide the layers based on these temperature changes. The troposphere is from the surface to 36,000 feet, and the temperature decreases with altitude in the troposphere. This is where the majority of flight occurs. The stratosphere is from 36,000 feet up to about 160,000 feet, and in the stratosphere the temperature remains constant in the lower part, and then it starts to increase with altitude. And that's because of the presence of ozone. Ozone absorbs heat from the sun, so the temperature starts to go back up in the stratosphere. Then the mesosphere is from 160,000 feet to 280,000 feet. And at this point, the temperature again starts to decrease with altitude. The thermosphere is above 280,000 feet, and in the thermosphere, temperature increases with altitude. This is a link to a pretty good video about the layers of the atmosphere. It's optional, but I highly recommend watching this video if you have the time. It's important to remember that atmosphere has mass. The definition of mass is the amount of matter that a body contains. There are a couple of different ways that we can use to measure mass. We can use the English system and measure it in slugs, or we can use the metric system and measure it in kilograms. Newton's second law says that a force equals a mass times acceleration. And if we think of gravity as acceleration, we can say acceleration equals g, where g is the acceleration due to gravity. So force can equal weight, where the weight is a weight of a given mass due to gravity. And we can measure that force in either newtons or pounds. So what are the properties of the atmosphere? Well, the atmosphere has pressure, and that's defined as a force exerted on a given area. We can measure pressure in millibars, we can measure it in pounds per square inch, or in inches of mercury. Temperature is a measure of either hotness or coldness. And remember, temperature is a measure of average kinetic energy. Kinetic energy is the energy of movement. So as the temperature increases, the molecules in a given volume of air actually start to move faster, and that movement is translated into heat. So remember, temperature is a measure of average kinetic energy, or the energy of motion. We measure temperature in either Celsius, which is the metric system, or Fahrenheit, which is the English system. Another property of the atmosphere is density, and we represent density whenever we look at an equation by the Greek letter rho. So whenever you see the Greek letter rho, think of density. The definition of density is the amount of mass or the number of molecules in a given volume of air. And we measure density in either kilograms per meter cubed, which is the metric system, or slugs per foot cubed, which is the English system. Atmospheric pressure is measured in inches of mercury with a mercurial barometer, in which mercury is forced up a barometer tube by the pressure of outside air. The International Standard Atmospheric Pressure in inches of mercury is 29.92. We can think of atmospheric pressure by considering 3 5-pound steel bars stacked end on end. The bars are about 1 square inch, so the pressure at the bottom of the 3 bars is 15 pounds per square inch. The pressure beneath the next level of bars is about 10 pounds per square inch. So as we move up, the pressure decreases. At the top level, the pressure is just 5 pounds per square inch. Now compare that to a vertical column of air, the same cross-section of 1 square inch that extends from the surface or sea level up to the upper reaches of the atmosphere. This column actually weighs 14.7 pounds per square inch. The pressure decreases with altitude. Since there's less air above it, just like with the steel bars, the pressure decreased as we moved up. The decrease in pressure with altitude is a key element in the operation of the pedostatic system in the aircraft that measures altitude, measures vertical speed, and measures airspeed. So knowing this about the atmosphere, we can predict what's going to happen physiologically due to these changes in pressure. If you've ever driven up and down a mountain range, you may have noticed that the pressure in your ears will change, and that can result in pain. Imagine the feeling at 40,000 feet. So remember that temperature is the energy of movement, kinetic energy. So when we're at 0 degrees Fahrenheit, which is below freezing, does that mean all heat is lost? Does that mean that all kinetic energy stops? No, the answer is no. There is still some molecular motion at 0 degrees Fahrenheit. Absolute zero is actually measured in Rankine, and absolute zero is minus 460 degrees Fahrenheit. So when we talk about temperature, we'll talk about measuring it in Rankine. And remember, Rankine equals Fahrenheit plus 460 degrees. Now, to understand the gases in the atmosphere, we have to understand 3 laws: Boyle's law, Charles' law, and the ideal gas law. Boyle's law states that the volume of gas is inversely proportional to the pressure, given a constant temperature. Now here's a good illustration of Boyle's law from NASA. It states that for a given mass at a constant temperature, the pressure times the volume is a constant. So P times V equals C. So what that means is, as pressure increases, volume has to decrease. And as pressure decreases, volume has to increase. If we scroll down in this illustration, we can see this illustrated. So as the volume increases, pressure decreases. As the volume decreases, pressure increases. Now, Charles' law says that the volume of gas is directly related to the temperature of the gas at a constant pressure. So in this law, we're keeping the pressure as a constant. So Charles' law says that if we keep pressure constant. Temperature, as temperature increases, the volume of gas will increase. As temperature decreases, the volume of gas will decrease. NASA gives us a good illustration of Charles' law. They call it Charles and Gay-Lussac's law. And it states that for a given mass, keeping pressure constant, the volume is directly proportional to the temperature. So if we scroll down, we can see that illustrated. So as you can see, with a constant pressure, as temperature increases, so does volume. Now we can combine Boyle's and Charles' law to get the ideal gas law. And the ideal gas law states that pressure, volume, and temperature in an ideal gas are related to a simple formula called the ideal gas law. And that formula is PV equals N times R times T, where P equals the pressure of the gas, V is the volume, T is the temperature, and N is the number of molecules or moles in the gas. R is a constant. It's called the gas constant. Again, NASA has a very nice illustration of the ideal gas law on this link. NASA calls the ideal gas law the equation of state. And the equation of state includes density, represented by ρ, pressure, represented by P, temperature, represented by T, volume, represented by V, and mass, represented by M. And as you can see, they combine Boyle's law, pressure times volume equals a constant, with Charles' law, volume equals a constant times temperature. It's not important for you to be able to derive these equations. Just understand that the final equation is P equals R times ρ times T. That's the ideal gas law, or the equation of state. So pressure equals R, a gas constant, times density times temperature. Now when we look at the ideal gas law, we'll consider volume and weight as well, or mass. So we'll start with PV equals WRT, where P equals pressure, V equals volume, and W equals weight or mass. So when we consider the ideal gas law, we'll assume temperature is in Rankine, and R is the universal gas constant, shown here. We know that pressure and temperature both decrease with an increase in altitude. So what effect does this have on density? How do we use the ideal gas law to solve for density? So the ideal gas law again is PV, pressure times volume, equals weight times the gas constant times temperature. So we don't have density in here. So how do we solve for density? Well, we know that weight equals mass times gravity. So we can change the W in PV equals WRT to mass times gravity to get PV equals mass times gravity times the gas constant times temperature. If we wanted to solve this new equation for pressure, how would we do that? Well, we could divide both sides by volume. If we divide both sides by volume, volume cancels out on the left side of the equation. So we get P, or pressure, equals mass times gravity times the gas constant times temperature divided by the volume. So now we have pressure equals mass times gravity times the gas constant times temperature divided by volume. So how do we solve for density, or ρ? Well, remember, density equals mass divided by volume. And we have mass divided by volume in this equation. So we can change it to pressure equals ρ times gravity times the gas constant times temperature. Now we can solve for rho. Now to solve for rho, we can divide each side of the equation by gravity times the gas constant times temperature. When we do that, it cancels out on this side, the right side of the equation, leaving rho by itself. So we have rho equals pressure divided by gravity times the gas constant times temperature. Since both R, the gas constant, and G, gravity, are constants, we can multiply them together to get another constant. So when we do that, we get this value here. Now all we need is pressure and temperature. And we can use standard pressure, which we know is 14.7 pounds per square inch, or if we want to use an absolute unit or a basic unit, 2,116.2 pounds per foot squared. So standard pressure is 14.7 pounds per square inch, or 2,116.2 pounds per square foot. Standard temperature at sea level is 59 degrees Fahrenheit, but we have to use an absolute value in Rankine. So remember, Rankine is Fahrenheit plus 460. So that temperature in Rankine is 519 degrees. So when we plug these figures in using the standard pressure at sea level and the standard temperature at sea level using the constants, we get rho equals 0.00238 slugs per square foot. That is the standard density at sea level. Remember, we haven't factored in humidity in this equation. The density is standard density at sea level, and it's only valid in dry air. So the equation rho equals P over GRT tells us that changes in pressure and temperature can affect density. We know that temperature and pressure decrease as we climb in the troposphere. So if temperature decreased faster than pressure, density would increase, but we know that's not the case. So pressure actually decreases faster than temperature. As we climb, density decreases as a result. Now humidity is the amount of moisture in the air, and absolute humidity is the mass of moisture in a given volume of air. When we say saturation, that's the point at which air can hold no more moisture, and that varies with temperature. It's called dew point. Relative humidity is the ratio of the actual amount of moisture in the air to the maximum possible amount of moisture that air can hold. So when you hear the term 70% humidity, that's relative humidity. That's the ratio of the amount of moisture that's actually in the air to the maximum amount possible at a given temperature. So which weighs more, air or water? If we add water to the air, how does that affect density? Well, you would think that adding water to the air would make it more dense. But if we look at Avogadro's law, it states equal volumes of any gas at the same pressure and temperature contain the same number of molecules. So at the same pressure and temperature, oxygen contains a molecular mass of 32, nitrogen contains a molecular mass of 28, but H2O, or water, only has a molecular mass of 18, less than oxygen and nitrogen, which, as you know, is 99% of the atmosphere. So since water has a lower molecular mass than oxygen or nitrogen, if we add water to the air, it actually becomes less dense. Just some terms to remember: the International Standard Atmosphere, or ISA, is the internationally agreed upon distribution of temperature, pressure, and density. So in the early days of aviation, the international community got together and decided what the standard sea level temperature, pressure, and density would be, so everyone could work from the same basis. Does ISA, or the International Standard Atmosphere, exist anywhere? No, it doesn't. It very rarely, if ever, exists. So what would cause the actual atmosphere to differ from ISA? The answer is any difference in temperature, pressure, or density. It's going to differ, all three of those values will differ on any given day. So why doesn't the Earth's atmosphere just float into outer space? What keeps the atmosphere attached to the surface of the Earth? And the answer is hydrostatic equilibrium. In the atmosphere, as you climb in altitude, pressure decreases, and that pressure difference causes an upward force called a pressure gradient force. That force is balanced by the force of gravity, and that keeps the atmosphere bound to the surface of the Earth. Here's a link to an optional video that you can watch further explaining the properties of the atmosphere and the flight environment. And you can watch that if you have time, but as I said, it's optional. The next presentation will be on the pedostatic system. We'll learn how the properties of the atmosphere actually work to help us measure altitude, measure our speed of climb or our speed of descent, and also help us measure our airspeed.